Hello, everyone. Welcome to today's Explainer Masterclass. I am absolutely thrilled to have all of you international engineering students joining me today. We are going to explore the fascinating, sometimes wild world of industrial automation. My main goal for us today is to help you truly understand how engineers take a chaotic, unpredictable process and bring it under perfect, reliable control. We're going to build this step by step, so please don't worry at all if these concepts are totally new to you. We'll get there together. But real quick, before we dive into the math and the machines, I want to warmly acknowledge the producer of our excellent source materials for today, Tiaja Kanene, Dr. Nima Madian. Because of these beautifully designed diagrams, we have a really clear visual roadmap to guide our learning in this session. Okay, so here is our syllabus for today. First, we'll start with the basics, our core engineering vocabulary. Then we'll move on to the physical control logic and the actual hardware we use in the factory. And finally, we'll tackle complexity by putting it all together into real-world systems. All right, part one. To build a great control system, we first have to understand the chaos. We literally cannot design a solution until we truly, deeply understand the problem we're trying to solve on the factory floor. So imagine you're walking through a chemical plant, and you look up at this massive distillation column connected to a huge mixing tank. You will see these everywhere in oil refineries. Now, just imagine for a second, what happens if the temperature or the pressure inside this giant metal tower goes completely out of control? Best case scenario, it ruins the product. Worst case, it could be incredibly dangerous. And that right there is exactly why control engineers are so essential. We have to tame this machine. Look at what happens without us. An uncontrolled process, which you can see as that erratic, wild red line, just violently crashes outside of our safe target corridor. Why? Because of external disturbances, like maybe a sudden freezing rainstorm outside, or internal shifts. But when we add a controller, that smooth blue line, the system constantly calculates the error signal. That's just the difference between where we are right now and our desired target. It then takes immediate action to gently guide that temperature back to safety. It keeps everything smooth, stable, and safe. Let's break this down into a block diagram. At the very heart of our system is the process. Think of that as our chemical tank. Feeding into it, we have our inputs. The control variables are the things we can easily change on purpose, like turning a valve to add heat. But then we have disturbances. Those are the things that sneak in and mess us up, like a sudden drop in outside temperature. Flowing out of the process, we have our outputs, which is what we actually measure, like the final liquid level. Understanding how these variables interact is step one in automation. Let's formally define these terms because, trust me, you will definitely see them on your exams. The trickiest but most important concept here is state variables. I want you to think of state variables like taking a perfect high-speed photograph of a moving car. If you know the car's exact speed, its exact weight, and its exact location at that specific fraction of a second, you completely know its state. In a factory, the absolute minimum set of conditions that perfectly describe what the system is doing right this second, those are your state variables. Excellent. Now that we've got our vocabulary down, let's jump into part two. How do engineers physically build the systems to fight off those disturbances? What actual physical hardware are we installing? Well, every single control system in the world relies on three very simple pillars: measure, decide, and act. First, we use our eyes, our physical sensors, to measure what is happening. Next, we use our brain, the logic chips, to decide what we need to do about it. And finally, we use our hands, the mechanical valves or motors, to act and change the process. Measure, decide, act. It's just a continuous, never-ending loop. Let's compare two different ways to do this. In manual control, a human operator physically stands there, reads a dial, thinks about it, and then turns a heavy wheel by hand. In automatic control, a computer handles that entire loop for us. But here is a really crucial insight for your future careers. Both of these systems usually rely on the exact same physical pipes, tanks, and valves to get the job done. We are simply swapping out the human brain for a microchip. Everything else is pretty much the same. So, let me pause here for a quick conceptual question. Think about that measure, decide, act loop we just covered. If the sensors are our eyes and the valves are our hands, what specific piece of industrial hardware acts as the brain of this whole operation? Take a second to think about it. If you guessed the controller, you hit the nail right on the head. Let's trace how that signal moves in the real world. First, the sensor detects the physical temperature. Then, the transmitter takes that raw reading, conditions it, and pushes it through the electrical wires. Next, the controller, our brain, receives it, computes the error, and decides exactly what to do. Finally, it shoots a command down to the final element, which is usually a physical actuator or a valve, telling it to actually open up or close down the flow of liquid.
Now, how do we actually wire these components together? We basically have two architectures. An open-loop system just tells the actuator what to do, but it's completely blind. It never looks back to check if the job was actually done right. A basic kitchen toaster is an open loop. It just heats up for 2 minutes whether your bread is perfect or completely on fire. But modern industry? We require feedback control, which is a closed loop. Notice how the sensor takes the output and feeds that data backwards into the controller? That is feedback. The system is constantly checking its own work and self-correcting. And for dynamic, messy environments, that is absolutely essential.
Once we have a closed loop, we generally have two different goals. In tracking control, the controller forces the process to chase a target that keeps moving, like a robotic assembly arm quickly moving to different weld positions on a car door. But in regulating control, our set point is just a static, flat line. Here, the controller's only job is to fight off disturbances to stay on that line, kind of like an industrial air conditioning system fighting off the blazing summer heat to keep a server room perfectly cool.
You guys are doing great. Now, we're moving into our final section, complexity and synthesis. And I have to warn you, real-world engineering is a whole lot messier than drawing isolated single loops on a blackboard. Because real systems are so complex, we have to follow a very strict blueprint. We start with the analysis phase. Step 1 is process definition. What are we actually trying to achieve here, and what are our absolute safety constraints? Step 2 is variable identification. We map out every single input, output, and disturbance. As engineers, we have to do all this careful mapping on paper before we ever touch a single piece of hardware. After we analyze, we move to the implementation phase. Step 3 is hardware selection. Now we're picking out the physical sensors, and we're sizing the valves to make sure they are actually strong enough to control the fluid flow. Finally, step 4 is algorithm design. This is where we write the actual logic into our PLCs and computers to make sure the system responds smoothly without violently vibrating or becoming unstable. Let's actually apply this blueprint to a real multivariable industrial process. Here's a mixing tank. We don't just care about one single thing here. We have to simultaneously control the liquid level, labeled H, and the liquid temperature, labeled T. We have one physical valve bringing in cold fluid and a totally separate valve bringing in hot fluid. So we essentially have two controllers trying to do their jobs at the exact same time on the exact same tank. And that brings us to a massive problem in engineering, which we call the coupling dilemma. Imagine you're taking a really nice warm shower, right? And suddenly, someone else in the house flushes the toilet. The cold water pressure drops, and instantly your shower becomes boiling hot. That is physical interference. In our industrial tank, if the level controller decides to open the cold valve to raise the liquid level, it accidentally drops the tank's overall temperature. So one control loop is literally acting as a massive disturbance to the other loop. I really want to pause here and highlight this because it is a very common mistake I see students make on exams. Please remember this. Do not fall into the trap of thinking that one valve changes only one variable. In the real world, everything is physically connected. When you design a system, you have to use advanced mathematics to predict and account for this inherent physical interference. And beyond that coupling issue, we face two more huge hurdles out in the field. First, modeling errors. The beautiful math we do on paper? Yeah, it almost never perfectly matches the messy physical reality of the factory. Our controllers have to be robust enough to survive those math errors. Second is nonlinearity. A physical valve behaves very differently when it's 20% open compared to when it's 80% open. The water just flows differently. Standard math really struggles with that, which is why we have to design smart, highly adaptable systems. So, let's synthesize. Let's bring the whole shebang together. This control dashboard right here, this is the blueprint of mastery. Our variable matrix helps us map the chaos. Our measured decide act feedback loop gives us the logic to fight it, and the physical mixing tank shows us the harsh reality of coupled physical hardware. Effective process automation is the architectural discipline of tying all three of these domains together robustly. Let's quickly review our key takeaways from today's explainer. First, always use a process matrix to clearly separate what you can control from your disturbances. Second, remember that closed feedback loops use the measure, decide, act sequence to constantly self-correct. Third, multivariable systems like our mixing tank suffer from physical coupling. Always remember the shower analogy. And fourth, Real-world systems must be intentionally designed to survive mathematical modeling errors and physical nonlinearity. Now, for your homework and to fully prepare for your upcoming exam, you need to review today's explainer notes and write out 5 multiple-choice questions testing these definitions. I also want you to solve 3 conceptual scenarios, prepare 2 calculation problems based on the tracking versus regulating graphs, and finally, be ready to discuss 1 real industrial case study, similar to our mixing tank.
All right, to wrap up, I want to leave you with one deep, provocative question to really test your conceptual understanding. If a feedback sensor completely fails in a coupled, multivariable system, what is the immediate physical consequence on the entire plant? Really think about how a failure in the measure step completely blinds the decide step and how physical coupling will spread that error everywhere. Review your notes, discuss this with your classmates, and we will kick off our next session with your answers. Thank you all so much for joining this masterclass. Keep studying hard, and I will see you next time.